All right, back from break. We started looking at thermodynamics. The big news here, we're starting to look at chapter 17. 17, 18, 19, and 20 will be covering a set of topics that we broadly refer to as thermodynamics, and that's how heat and temperature, thermal energy, is involved in properties of different sorts of materials. So let's take a look and see. Right now we're going to be looking at the ideal gas law. So when we have a gas, we said what kind of sets gases apart from liquids and solids is that the gases can be compressed relatively easily. And so if gases can be compressed, that means that we're going to have to bring in pressure as well as volume. Pressure is going to make a difference in terms of what volume the gas is going to have. So it's not enough to relate volume and temperature. We have to bring pressure into that formula, into the formulas that we want to use. So in any case, there's a number of different relationships that we can show for these gas molecules. Now there's what's called Boyle's law, and Boyle's law was the idea that if we keep the temperature constant, that the pressure and volume are inversely related. They're inversely proportional to each other. What that says is, if the volume shrinks by a factor of 2, the pressure goes up by a factor of 2. If the volume increases by a factor of 5 for a collection of molecules, the pressure goes down by a factor of 5. And so this is just based on the idea if you've got a bunch of gas molecules in a region, in a container, and they're bouncing back and forth, the pressure is based on how frequently they collide with the walls or how frequently they collide with each other. And so if we have these expansions that take place at constant temperature, it still means that the collisions of gas molecules with the walls or with each other are less frequent. The molecules are more spread out, and as a result, the pressure will go down. So here's another relationship that we can write down for these gas molecules. What we can do, this is an interesting way. This is what we're going to be doing in lab. Actually, oh, this is a little different. Okay, here the pressure is constant. So in any case, if we're at a constant pressure and we lower the temperature on a bunch of gas molecules, what we can observe is it shrinks. So if we have a bunch of gas molecules in a flexible container, like a balloon, for example, where the pressure is staying roughly constant, as we cool down the air molecules in that balloon, the balloon shrinks, right? The balloon will contract, and the air molecules are in a smaller space. So at lower temperatures, the gas molecules are moving more slowly. So that's one of the first thermal connections we want to make. Temperature is going to give us an indication of how much kinetic energy or how fast the gas molecules are moving. So in this example, what we could do, and this is a little different from the lab we're doing is in terms of pressure differences when the volume is constant. In any case, as we cool things down, we can see the volume decreasing. Now, we're not going to be able to take those gas molecules all the way to absolute zero because that's really cold. And first of all, we don't have the equipment set up to take it all the way down. But maybe more importantly, we can't take the gas molecules down to absolute zero and have them remain gas. At some point, they will either liquefy or they will solidify. These molecules will liquefy and freeze into a solid. So I can't keep the gas molecules being gas molecules all the way to absolute zero. But what we can do is we can collect a bunch of data over a temperature region, and then we can extrapolate. So we can extrapolate that line and estimate if we continue to have a linear drop-off, at what point would we have no volume at all, and that will approximate absolute zero. So that's what the setup here is referring to. And again, measurements that we've done, not necessarily these, but indicate that absolute zero is at minus 273.15. So earlier we talked about absolute zero a bit, and we said that absolute zero, the classical definition of absolute zero is the temperature at which all the energy has been removed from the molecules. There is no translational energy, there is no rotational energy, there is no vibrational energy. Turns out that's not quite true. We understand now that from quantum mechanics, which we'll see later next semester in Physics 3B, that the energies of the molecules actually are in what we call quantum states. And so what we can do is we can take the molecules down so that all of the molecules are in the lowest quantum state possible. But it turns out that even in the lowest quantum state possible, there is still residual energy. So absolute zero has a little different meaning to it. It means that, kind of the quantum definition is that everything has dropped into the lowest available quantum states. Now, for our purposes here in this course, we are going to continue to treat absolute zero as all the energy has gone to zero, there's nothing left. But again, next semester, we'll get a chance to go in and see what these minimum energies look like. All right, so the concept of absolute zero allows us to define a third temperature scale, the absolute scale of Kelvin. Now, we started out with Kelvin right away. So Kelvin is too important to leave even for a few slides. So we introduced Kelvin right away. In fact, when my friend and I, when we were in high school in our chemistry classes and they taught us about the Kelvin scale, we kind of made a promise that we would never use another temperature scale ever again. We would not use Fahrenheit, we would not use Celsius. We were only going to use Kelvin because Kelvin was the only reliable scale. Kelvin meant what it said. When Kelvin says zero, there is no energy left. Fahrenheit and Celsius, they're not reliable. They're not honest. When it's 0 Fahrenheit, there's still lots of energy left. When it's 0 Celsius, there's still lots of energy left. Only Kelvin is the reliable scale, and so right then and there, we promised we would never use another temperature scale, and that lasted for a few days, and then we were back using Celsius. So it's useful to have a Celsius scale. People are more familiar with it. Maybe with a lot of practice, people could adapt and start using a Kelvin scale, but I think the Celsius scale is here at least for the foreseeable future. In any case, when we're thinking in terms of temperatures of these gas molecules, you want to think in terms of kelvins. Okay, the temperatures have got to be in terms of kelvins, because what we're doing is we're saying this. We're saying that the pressure is proportional to the absolute temperature. The pressure is not proportional to temperature measured in Celsius or Fahrenheit. Pressure is proportional to temperature measured on an absolute scale like kelvins. And the volumes are proportional also to the temperature measured in kelvins. So that's what we got to use. Now the conceptual, this is, okay, so every once in a while I run across these examples in the notes, in the provided slides that are, to me, they're kind of interesting, kind of funny. Why should you not throw a closed glass jar into a campfire? Because you'll break the glass, I guess. Anyway, I think they're assuming that if you throw it in, initially the glass survives, but because it's closed, the gas molecules, the air molecules inside that container will expand and it will explode the glass. that increase in pressure will push the glass away, and by the time the glass fractures, it could be at a pretty high pressure. It could really drive that glass at a pretty high speed. So I know you were thinking this would be a sensible thing to do, but don't do it. Don't throw a closed glass jar into a fire. Not a good idea. I'm not sure what they're telling you in chemistry. I hope they're telling you the same. All right, we are headed towards the development of what we call the ideal gas law. You may have noticed that there have been a number of slides here kind of talking about pressures and volumes and temperatures and how they're all going to be related. Well, now what we're able to do is say this: the pressure times the volume should be proportional to the temperature. So now we need something to tell us how much gas we have inside there. Now, one possibility would be to say that the pressure times volume is proportional to the mass of the gas times the temperature. But we find out that gas molecules have different masses to them, and it's not actually the mass that determines what the pressure will be for a collection of gas molecules. You would think, I would think that's a sensible idea, is that if we got all these gas molecules moving around at some speed, it would be the heavier ones that would generate the most pressure. But it turns out that's not true, and that's because at the same temperature, the heavier molecules move more slowly, and the lighter molecules move faster. So it's not the mass of the particles that's important, it's how many gas molecules we have. It's the number of gas molecules that we want to put into the equation that we have here. It's the number of gas molecules. So the way nature works, when the energy is getting divided up, at a given temperature, roughly the same amount of energy is given to every molecule. The same amount of translational energy is provided for each molecule. Now, if you give all the molecules each roughly the same amount of energy, it turns out that the lighter ones are going to go faster and the heavier ones are going to go more slowly. So it's not proportional to the mass. That's not as useful. It's more useful to think in terms of the number. Now, we're going to go back and once again, we're going to introduce the idea of moles. And moles are a way to keep track of the number of molecules in a sample. Here's how it works. The value of 1 mole is 6.022 10 to the 23 particles. We saw that earlier in those earlier slides. And it turns out that 1 mole of hydrogen molecules has a mass of about 2 grams. A mole of neon molecules has a mass of 20 grams, and a mole of carbon dioxide has a mass of 44 grams. Where are these all coming from? Well, we have to look at the chemical formulas. The mole of hydrogen consists of each atom, each molecule within there, consists of 2 atoms, and each atom of hydrogen is about each mole of hydrogen is about 1 gram. So if I have a mole of molecules, that's 1 plus 1 is 2. Neon atoms stay independent. They don't chemically bond to other atoms. And so each individual neon is about 20 atomic mass units. 1 mole would be 20 grams. Now, carbon dioxide, I have to take 1 carbon and a couple of oxygens. Now, the most common isotopes by far for carbon and oxygen, the carbon isotope that's in highest abundance is 12, and oxygen is 16. So if I take a mass of 12 plus 16 plus 16, that adds up to be 44. once the molecules form, nature treats them as one object. So it doesn't give energy individually to the carbon and the oxygen and the oxygen. What happens is the carbon dioxide molecule, as one unit, gets an allotment of translational energy. So again, nature provides the same amount of energy on average to each molecule in the system. Now this introduces the idea of a molecular mass, or what I'm going to refer to as a molar mass. Molecular mass sounds like the mass of a molecule. I want to know what the mass is for an entire mole of the substance. So the number of moles that we have is equal to the mass of the sample divided through by the molar mass. So if I know, for example, let's say we have 200, let's say we have 100 grams of neon, how many atoms is that? And so that's going to be 100 divided by 20, that's going to be 5 moles, and each mole is 6 times 10 to the 22. So we can count, we can use this approach to actually go in and just count how many molecules are in the sample. So here's some more, in addition to that example. So 1 mole of any type of molecule corresponds to 6.022 10 to the 23rd. Now, if it's atoms we're counting, then it's that number of atoms, but if it's molecules we're counting, it's that number of molecules. 1 gram is the same thing as Avogadro's number of atomic mass units. So let's think in terms of the isotopes of neon. So these are the stable isotopes. Neon has an isotope that is neon 20, which has 10 protons and 10 neutrons. So each atom is about 20 atomic mass units. The 21 isotope has an extra neutron. Now it's still neon because it has 10 protons. Any nucleus that has 10 protons is classified as neon. It will behave chemically as neon. And so each atom now of this isotope would be 21.0, roughly. There's more numbers than that. This has been rounded. There's an isotope of neon that's 22, and it consists of 10 protons and 12 neutrons. Each proton or neutron is approximately 1 atomic mass unit. So what that leaves us with is an individual atom that has roughly 22 atomic mass units. Now let's look at abundances here. Well, first of all, this is the mass for 1 atom. For if I have an entire mole, then the atomic mass units get changed, and now we can write that in terms of grams, is the way it works. Now the abundances, the neon 20 makes up a little over 90% of the neon in nature. The neon 21 makes up less than 1%, and the neon 22 makes up about 9%. So if we take these numbers and multiply by these abundances, we get an average molar mass of 20.18, and that's what's in the periodic table. So the periodic table masses are averaged over the isotopes that are present in the samples, in the naturally occurring samples. So they don't show masses for individual isotopes, they're averaged over the different isotopes. Something just to be aware of. What happens is when you're looking at a collection of atoms, sometimes all you need are just the average properties, but when we're starting to look at individual molecules, the different isotopes will have slightly different properties. For example, a neon at the same temperature, going back to this example, at the same temperature, each of these individual isotopes of neon end up with roughly the same amount of kinetic energy on average. Now if you give the same amount of kinetic energy to each of these atoms, the neon 20 is going to go faster because it's a little bit lighter. So everybody gets the same kinetic energy. The heavier atoms go slower, the lighter atoms go faster. All right, here it is, the ideal gas law. It's beautiful. It says that for a sample of gas molecules, the pressure times the volume is equal to the number of moles times a constant. So we've thrown a constant in there, and the constant in there is arbitrating all the units and all the unit scales that we've come up with. So R you can think of as accommodating all the units that we've defined, and then there's a factor of temperature. Now, R is called the universal gas constant, and this is one of those misnomers that we, I guess we just have to put up with it. Big R is used for all different phases. It's not exclusive for gas molecules. It gets used for liquids, it gets used for solids. It most often shows up when we're looking at ideal gases, and so for whatever reason, it has come to be called the universal gas constant, but it's not limited to gases. Okay, so maybe that's the way to say it. It's the universal gas constant that's not limited to gases. It works for liquids and solids too. So in standard units, big R is 8.314 joules per mole per Kelvin. And what we can start to see in there is, you know what big R is doing? It's kind of a conversion between energy and temperature. So if you tell me the temperature, I can tell you how much energy individual gas molecules will have on average in the sample. All right, so let's look at some variations of the ideal gas law. This is in different units. These are units that are commonly used in chemistry. I would highly recommend that you work in terms of standard units. You'll notice that if you're in chemistry classes, often what they'll do in different parts of the course, they'll switch back and forth. They'll work in terms of liters and atmospheres. Now those are not standard units for pressure or for volume. And then they'll switch back over to joules when they need to use some formulas that are requiring standard units. And I would say, you know, you only need one set of units. We could just stick with this. Now, calories, for whatever reason, and I dearly love our textbook, but one of the differences I have is that they do like to come back and use calories a lot, and I think calories are on their way out. When you look at food items in the store now, you'll notice when you're looking at nutritional numbers that they'll have the energy content listed in kilojoules. So I'm hoping that calories is on its way out, and we'll just work in terms of joules. I hope. All right. So some variations on the ideal gas law. First of all, there's PV equals nRT, where big R is the gas constant, and little n is the number of moles. Now, we could work directly in terms of the number of molecules. What if we don't decide to use these moles that we've been introduced to? What if we just go back and count the number of molecules? Well, it can be done, so it's not that difficult to go back, except when you're working in number of molecules, you spend a lot of time using scientific notation. So it slows things down a bit because there's a huge number of molecules in all the samples that we look at. But you'll see some instances, I think we've got some examples coming up, where we do go back and just flat out count the number of molecules. Now when we do that, we need a different constant. And the constant we use for this is what's called Boltzmann's constant. And I apologize, but for Boltzmann's constant, we use a little k. Now, let's see, maybe that's too soon to be using little k for something else, because let's see, back in mechanics, chapters 1 through 16, little k was used for a spring constant, little k was used for a force constant, and little k was used for a wave number. That's a lot of uses for little k, and now we're going to use it for something completely unrelated. This is thermodynamics. This is Boltzmann's constant. Boltzmann's constant is considered a fairly fundamental constant that we work from a lot. And so Boltzmann's constant, 1.38, 10 to the minus 23, there's the scientific notation. So let's see, where else did I see 10 to the 23? Oh yeah, that was in the definition of a mole. So if I use the number of atoms, I'm going to have numbers like 10 to the 23 going on, and that will cancel out with the 10 to the minus 23 in Boltzmann's constant. So bottom line is, for most everyday size samples of materials, using big R is probably easier, but you should always be prepared to go back and use Boltzmann's constant as needed. Now the other items here are pressure, volume, and temperature. What are standard units for pressure? Pascals, or joules per cubic meter, that works. Volumes are in cubic meters. Temperatures are always in Kelvin. Kelvins only. This is an energy equation. Pressure can be written in joules per cubic meter. When I multiply pressure times the volume, I get units of energy. Those are joules on the left side. What's on the right side of the equation? Well, this is number of moles. R is in joules per mole per Kelvin, and temperature is always in kelvins. And so that says each side of the equation, the units simplify down to energy units. It's kind of an energy formula that we're looking at here. So the ideal gas law, let's practice using that. Okay, so standard temperature and pressure is defined as 0 Celsius, or 273 kelvins, and pressure of 1 atmosphere is boy, they got that one wrong, huh? So 1 atmosphere pressure is 101.3 kilopascals. I didn't see this going through the slides. This is 1.013? I don't think so. This is 1.013 times 10 to the 5th. So this number is off by a factor of 100,000. So get that corrected. If I remember, I will go back and correct something there. So example 17 says, what's the volume of 1 mole at standard temperature and pressure? And so we can use the ideal gas law and go ahead and take a look at that. So I'm going to say the volume of 1 mole at standard temperature and pressure. So 1 mole would be 6.022, 10 to the 23 gas molecules. It doesn't matter which compound we're looking at. The pressure would be 101,300 newtons per square meter, or joules per cubic meter. The temperature, Celsius, won't work. I got to use 273.15. So now I'm going to bring in the gas law, the ideal gas formula, and solve for V. I'm going to put all the numbers in. Everything's in standard units. 1 mole, 8.314 joules per mole per Kelvin for big R, 273.15 Kelvin for the temperature, and 101,300 joules per cubic meter. The volume works out to be 0.0224 cubic meters. There's 1,000 liters in a cubic meter, so that would be 22.4 liters. So that's at standard temperature and pressure. Now that's something that students learn in chemistry, so a lot of times I have students that come in and they say 1 mole of gas is always equal to 22.4 liters, and that's not true. This volume only happens under these conditions. That is not a general statement. So it's only at 0 Celsius and at 1 atmosphere pressure we end up with that number. So don't use this generally. But here is our standard box, See all those gas molecules bouncing around inside there? So we've got a volume, there's a certain pressure being generated by the gas molecules. The pressure is a property throughout the sample, as we learned back in chapter 13. It's not just the molecules hitting the sides, it's the molecules interacting all through the sample. If I put something inside there, the molecules are going to be bouncing off that object. There's a pressure that's maintained throughout. The gas molecules are at a certain temperature. Now, being at a certain temperature means, on average, they have a certain amount of kinetic energy. We're always going to have some molecules that are going faster, some molecules that are going slower. No big deal. After a few collisions, the faster ones are going slower and the slower ones are going faster. But on average, we can figure out how much energy they have by knowing the temperature. Finally, the number of molecules is given to us in terms of numbers of moles. So that is the idea. Here is a helium balloon, and we're at a helium balloon, a helium party balloon, sorry. I thought it was a balloon party, but it's a party balloon. I got to read more carefully. Assumed to be a perfect sphere. So I've got a helium balloon. It's a perfect sphere. Has a radius of 18 centimeters. It's at room temperature. Its internal pressure is 1.05 atmospheres. Now the pressure inside has to be a little bigger so that we can push out the balloon, and it can make the balloon maintain that volume. All right. If I had 1 atmosphere inside and 1 atmosphere outside, the balloon would go kind of flat. But with a little extra pressure inside, the balloon will push out. Find the number of moles, that's interesting, and the mass of the helium. Oh, I like this problem. That's a hint. I do like this problem. So here is a sample of helium inside this balloon. The balloon has a diameter of 36 inches, so it's a pretty good sized balloon. It's a party balloon, right? So it's got to be fun. And it's 36 centimeters across. I'm going to put the numbers, plug the numbers in to my volume formula, and I'm going to put everything in standard units along the way. The volume of that balloon works out to be 0.0244 cubic meters. And now what I can do is I can take the pressure given in atmospheres. Atmospheres aren't the units I want. I want standard units. So I can convert that into standard units, and 1.05 atmospheres is 106,365 joules per cubic meter. Those are standard units. And then the temperature, Celsius, you can't trust Celsius. Celsius doesn't mean what it says. Kelvin is the serious absolute temperature scale. I'm going to work in Kelvin. So I got to get rid of the Celsius and move to Kelvin. Kelvin, when it says 0, it means 0. So the number of moles then would be PV over RT. And, you know, it took a few steps. And it took a few steps because I had to check off each one of the units and each one of the units' conversions and making sure that I've got those covered. Now that I've done that, I can put all the numbers in. The cubic meters here will cancel the cubic meters, the joules will cancel the joules, the kelvins will cancel the kelvins. All that's left are the moles. And the moles are in the denominator of a denominator. And that means that the moles will pop back up to the top. So they're going to show up in the numerator. And when I run all the numbers, it says that I have 1.067 moles. What do you think? Okay, so practice these. Don't just watch them. There's a lot of steps here, and you want to be able to practice these until you very smoothly, without hesitation, go from one step to the next. That's the idea. A lot of times students will say, but I did those problems. I'm not going back and redoing them. I already did them. I don't have to do them again. But other students will tell me, you know, it's all about rehearse, rehearse, rehearse. So I have students that come up and say, you know, their strategy, which I'm going to say is very effective, is that you do a set of problems, and then you come back the next day and you practice going through them again. Not that you've memorized them, but you've learned the skills in solving them. So definitely think in terms of going back and repeating these problems and explain to yourself at each step why you're carrying out that particular calculation. That's, I want to say that's how it's done. That's how you really learn and really internalize this information and these skills. Okay, that's my lecture for the day. The molar mass of helium, I looked that up on a periodic table or something. It said it was 4.0026 grams per mole. So the mass of this is 4.27 grams. I have a balloon that's this big. It's a little over 1 atmosphere pressure. And it's at a temperature of, 20 Celsius. And it's got 4 grams of helium. And that doesn't sound like much. 4 grams of helium is enough to maintain all that pressure. A little later in the course, we'll learn techniques where we can calculate just how fast those 4 grams of helium, the individual atoms, are moving. So we'll get a chance to go in and determine that. What's the mass of air in a room? Estimate the mass of air in a room. Let's say the dimensions are, 5 meters is about right. 3 meters, 3 meters, maybe more. No, actually 3 is very good. So I'm just looking at the room here, and from wall to wall, it's about 5. 5's pretty good. They wrote this problem for this room. 2.5 meters, yep, that's this room. Well, it's not this room. It's the front part of this room. And so what's the mass of all the air in here? Now, okay, this is where I draw the line. I can't go along with this. They want us to calculate the mass of the air at standard temperature and pressure. I don't like standard temperature and pressure. The temperature's fine. 20 degrees Celsius, I have no problems with that. I'm sorry, it is the temperature that I don't like. What I wanted to say is that the pressure I have no problem with. Standard pressure is 1 atmosphere, and I like 1 atmosphere. I like 1 atmosphere a lot. But the standard temperature is 0 Celsius. Now, almost everything defined in physics and engineering uses 20 Celsius as the standard. It's just standard temperature and pressure where they move it down to 0. That's too cold. I don't want to go there. So, and the air molecule, the temperature in here is not 0. So why would we want to calculate that way? So I'm going to change this. Okay, and here's a reminder of what air is made out of. 78% nitrogen, 21% oxygen, 1% argon, variable amount of water vapor. I guess we'll come back. Okay, so the volume in this room is 5 times 3 times 2.5. So the volume we have is 37.5 cubic meters, not liters. Cubic meters. Cubic meters are like this. Cubic meters are big. And that's how many cubic meters we have in this front portion of the room. The pressure is 1 atmosphere. I like 1 atmosphere. 101,300 joules per cubic meter. The temperature I'm going to change. Sorry, STP. I'm not using 0 Celsius. I'm bumping up the temperature to 20 Celsius. So I'm going to bump up the temperature to 293 Kelvin, because that's more like what it is in here. And 0 Celsius, 0 Kelvin would be really cold. 0 Celsius is just too cold. So the number of moles of air molecules in the room are given by PV over RT. I put in my P, standard units, put in my V, standard units, put in big R, standard units, put in the temperature, that's in kelvins. What I've found is that in this part of the room, there are 1,559 moles of air. Now, if I multiply that by Avogadro's number, I will know how many molecules of air I have in this part of the room. Now, you might be saying, but wait a minute, you never took into account that the air molecules are made up of different compounds. Isn't that going to change your calculation? And the answer would be no. Because all the different air molecules in the room are in thermal equilibrium with each other. The air everywhere is essentially at the same temperature. That says that every individual molecule is going to contribute to the pressure equally. Okay, so each molecular species, let's say this a little differently. So on average, each molecule will contribute equally. We just have to know how many there are. And the number of moles will tell us how many we have total. Now that we know the total number, we can come back and say, well, 78% of those molecules are N2, 21% are O2, 1% is argon, and that tells us how many moles of each compound we have. So now we know how many moles of N2, how many moles of O2, how many moles of AR we have in the room. And taking the number of moles and then writing down the molar mass for each of these, that's the number of kilograms of nitrogen, this is the number of kilograms of oxygen, this is the number of kilograms of argon. We add those together. We have 45 kilograms of air just in this part of the room. 45 kilograms, that's like 100 pounds of air. I would have a hard time lifting all that air. And it's not such a big room. Air is substantial. We often think of air as just not much there, but there really is. Okay, 100 pounds of air, 45 kilograms of air in this portion of the room. Okay, good to know, right? All right. So you can see that the ideal gas formula. I have certain approaches that I feel like are the best way to learn how to use it and the best way to communicate with other people about the different numbers. So right here, okay, this drives me a little crazy. They actually put in the notes the volume of 1 mole of an ideal gas is 22.4 liters. No, it's not. That's only if the temperature was 0 and if the pressure was 1 atmosphere. Or if it's a different, you can find different combinations of temperature and pressure that will work, but in general, that's not true. So I crossed it out. I put in the cross out red line. Okay, so that doesn't work. Now, what about the second statement? If the amount of gas is fixed, if the gas molecules are not allowed to leave or come in, then P1 V1 T1 equals P2 V2 T2. That's true. So if we keep the same number of molecules, then the pressure times the volume divided by the temperature, that combination will remain the same. So for example, what would happen if I raise the temperature? Well, if I raise the temperature, either the pressure or the volume has to go up. Something's got to give, because I know that PV over T starts out at some value, and if I fiddle around with one of these, I have to compensate with one of the others. I have to change at least 2 of these. If I change one, I have to change at least one of the other values. Okay. Always measure T in kelvins. Yes, 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 yes. And pressure needs to be absolute pressure also. That's also absolutely essential. Okay, so the temperatures and the pressures have to be what we call absolute values. All right, you're ready to check your tires and find out what pressure is inside. So we got an automobile tire. It's filled to a gauge pressure of 200 kilopascals. Now that's at 10 Celsius. So it's kind of chilly outside. This person should put a jacket on or something because it's only 10 Celsius outside. It's kind of chilly. After a drive of 100 kilograms, the temperature has gone up to 40 Celsius. So the temperature of the tires is much higher, and presumably, the temperature of the air molecules has also gone up. So what is the pressure inside the tire now? Now this question is a little tricky, and so as you guys know now, you guys have enough experience with physics in these past 14 weeks, 12 weeks. So over the past 12 weeks, you guys have learned enough from your experience in physics to know that sometimes things feel like they got left out in the question. And so right here, let's list everything that we might need to know. First of all, they told us the pressure at the lower temperature is 200 kilopascals, and here is the lower temperature. I can't use Celsius, it's got to be kelvins. Now they say after driving for 100 kilometers, the temperature has gone up to 40 Celsius, which I immediately convert. I don't want to forget, I don't know how you guys are, but if I don't convert my temperatures and my pressures right away, I forget. So I do that right at the start. So this is in kelvins. They want us to find out what this pressure is. Now let's go back and look at the ideal gas law. Now if the number of moles has not changed, so the first assumption here is we have the same number of air molecules inside the tire that we had before. That seems reasonable. I seldom pump any additional air in my tire. I almost never do. And they seem to maintain pressure, so tires can be sealed pretty reliably. That says P1 V1 over T1 is equal to P2 V2 over T2. I could use ratios. So I'm going to say that the pressure that we have at the higher temperature is equal to the original pressure times, let's see how the ratios work. This is going to be V1 over V2, and this is going to be T2 over T1. Now, what is it? Do we know any information about the volume? And I don't. They didn't give us any volume information. I don't know how to judge or estimate the volume of this tire that they're talking about. You know what? They're expecting us to assume that the volume is unchanged. They're going to say a tire is actually pretty rigid. Now, you know, I've ridden bicycles a lot my whole life, and I know that when I pump up a bicycle tire, the tire gets bigger. So the tire, you know, bulges a bit. Car tires aren't like that, I guess, right? If you pump up a car tire, its volume is going to be changed very little. The car tires are very rigid and sturdy. So anyway, I think that's what they're assuming here. They're assuming that the volume before and after is the same, and that means this ratio drops out. There was no change in volume, no significant change. That becomes a factor of 1, a ratio of 1, and we can drop it out of the calculations. So now we're down to the original pressure times the ratio of the absolute temperatures. Now, if we're going from 10 Celsius to 40 Celsius, you might think that's a factor of 4, but it's not, because Celsius is not truthful and honest. We have to convert to an absolute temperature scale to gauge the temperature ratios. The temperature ratio is actually 313 to 283. Now that's not such a huge ratio. So you don't have to worry, oh my gosh, the temperature went from 10 to 40. That's 4 times the pressure in my tires. My tires are going to blow up. That's not what's going on here. Going to 313 divided by 283, that's only an increase of 10 or 11%. So the pressure, even over that, that's a pretty good sized temperature range. But the pressure is only going to go up about 10%. Now, that still may be something you want to keep an eye on in driving your car. So with that 10% increase, the pressure went up to 221. So it started at 200 and it went up to 221. Not a huge deal, okay? It went up about 10%. So if you're thinking of pounds per square inch, if you start at 30, at the higher temperature it's going to be 33. All right. Okay, this is fun, right? Now, we've been using what we call Avogadro's number, and there it is, 6.02 times 10 to the 23rd. Everybody should aspire to have their own number. That's Avogadro's. And yeah, it's just the number of molecules or atoms in a particular, in 1 mole of that sample. So if I have 1 mole of argon, if I have 1 mole of carbon dioxide, it's counting how many molecules are in, it's 1 mole is the same number. It's the 6.02 10 to the 23rd. Okay, 1 mole of any substance has that many molecules in it. So what happens then is we can take PV equals nRT, we did this on an earlier slide, and I can take out the number of moles and replace it with the number of molecules divided by Avogadro's number. That calculation will tell me how many moles, and then we can substitute in, there it is, Boltzmann's constant. So little k is Boltzmann's constant. I know maybe it's too soon, but it's no longer the wave number. There are going to be no wave numbers in sight for the rest of the semester. Chapter 17, 18, 19, 20, there are no wave numbers, there are no spring constants, there are no force constants until the final exam. Okay, so, but when you're looking at problems on the final exam, anything from chapters 1 through 16, K is going to be something else. It's going to be a force constant, but if it's thermodynamics, it's going to be Boltzmann's constant. All right? So you got to think thermodynamically when you're looking at thermodynamics problems. And that's the value, and we can get big R and convert it to Boltzmann's constant by dividing through by Avogadro's number. Avogadro's number is turning out to be a very useful conversion factor between many things. All right, I think we have a couple more examples here to take a look at. Example 14 says, use Avogadro's number to determine the mass of a hydrogen atom. And while we're at, well, let's just do one at a time. Here it is. The molar mass of hydrogen, now, that won't work. And so here's the reason why. Hydrogen consists of different isotopes. This isotope thing keeps getting left out. So I can't ask what's the mass of hydrogen. I have to ask what's the mass of a specific isotope. What's the mass of hydrogen 1 or what's the mass of hydrogen 2? So it turns out that the molar mass of hydrogen 1, so I'm just going to look at one isotope, and that one isotope has a molar mass of 1.0078. I'd better have this right. I'm going to have to go back and check. That is looking like maybe it came off the average from the periodic table. And if it is, I got to go back and change it. So if this is the molar mass for hydrogen 1, and then I divide through by Avogadro's number, it says that the individual hydrogen atom is 1.674 10 to the minus 24 grams, also known as 1.674 10 to the minus 27 kilograms. So I put it in both. How many this is the next question. I got to go back and check if I got the right numbers on that, because you got to do it isotope by isotope. You can't average over the isotopes to get the mass of an individual atom. So we got to go back and check that one. 1715, how many molecules are there in one breath? I don't know. It says one breath is, a liter? Okay, 1 liter of air. So what we're going to do is we're going to take 1 liter of air. I can do that, I think. So let's count. Let's use this version of the ideal gas law, PV over Boltzmann's constant. There it is. Here is the pressure, 1 atmosphere. Here is 1 liter written as cubic meters. A liter is 1,000th of a cubic meter. And then Boltzmann's constant, the temperature is at 20 Celsius. They didn't tell me, so I'm going to use 293 Kelvin. And here it is. It's a mixture of nitrogen, oxygen, argon, water, carbon dioxide, and it's at 2.51. It actually could be a fair amount of carbon dioxide, right? I wonder, what is the percentage of carbon dioxide in the air you exhale? And oxygen. It could be a lot of the oxygen is depleted. And that's an interesting question to look up. 2.51, 10 to the 22 molecules per liter of air. Okay, that was it. We are through chapter 17. I've got some things I got to look up and check. All right, and we'll leave it right here. All right, if you guys have any questions, this is a new set of topics. I hope this is going to be really interesting. Stop by office hours with whatever questions you guys have.